Hi, I'm Andy Davidson, founder of Financial Lifecycle Education, a not-for-profit that also goes by the name of FiCycle. And welcome to our discussion of data science and credit scores. As always, we're always talking about how we connect math to personal finance. Today's topic is Am I My Credit Score? And this is part 2 of a 4-part series about credit scores and data science. Financial Lifecycle Education Corp is, as I mentioned, a not-for-profit, and we engage in research, development of standards. We have a full Algebra 2 level course. We also have modules and various lessons. If you want to learn more about us, please go to the QR code. As I mentioned, this is about credit scores. We're further developing material about credit scores. And if you're interested in receiving any of the materials that we're developing, please go to this QR code and fill out the form. Thank you. So in part 1, we talked a little bit about odds and probability and some of the equations for converting between odds and probability. And then we also talked about log odds and the relationship between logs, odds, and the output of credit scores. And we found that a credit score is closely related to the log odds of people making on-time payments on their outstanding credit obligations. We also talked about the logistic function, which is from the function probability equals 1 over 1 plus e to the minus x, where minus x is the log odds, and how this was an important function for us to develop a credit score model. We also looked at some credit score data that we received from Experian, some anonymized data, and started to think about how do we transform this type of data into a score. We talked about that there are multiple steps that you would need to go through in order to do that, but it was a fairly complicated process, and it would make sense to look at a more simpler problem first. And that's what we're doing here in part 2. We're going to look at a car price example, and we're going to go through similar steps that we would go through for credit scores, but in a little bit easier model to develop. So we're going to identify our dependent variable, that is our y. We're going to create and evaluate some attributes, or x's. Then we're going to use a linear regression model. We'll assess that model, and we're going to make some predictions. Well, let's get to it. So here's the problem. We have prices of some cars with various mileage in the car years, and we're trying to predict the price of a car based on its mileage and its year. So the dependent variable is the price of the car, and the independent or explanatory variables are the mileage and the car year. And here you can see that we've graphed these things with the mileage on the x-axis and the price of the car on the y-axis, or the year on the x-axis, also the price on the y-axis. So we can see that a car value declines with the mileage, but increases with the year. So we could work with mileage and car year, but really, if we try and think about it, like what are we really trying to measure with those variables? So what we're really trying to look at is the age of the car. So like next year, the same model year will be the same age, but its age, this model year will be the same. Like let's say 1924 car, 1925, still a 1924 car, but it's a year older. And therefore, the price would likely be lower. And then also, rather than looking at mileage, it might be better to look at if the mileage is higher or lower than you'd expect for a car of that age. So that's what we're going to do, is we're going to transform our original variable into what we're going to call attributes. And our attributes are going to be age and excess miles. Now, how are we going to model using that? So we're going to use a tool called a linear regression. And a linear regression uses what we know about lines. So on the left-hand side, we show the equation of a line, which is y equals mx plus b, where m is the slope and b is the intercept, where x equals 0. So we're going to do the same thing on the right-hand side, but in regression, we use different terms. Often we use alpha and beta. So we're going to say y equals alpha plus beta times x. So alpha is the intercept, beta is the slope. And then because it's a model and we're not sure we have the exact result, we're going to add an error, which is sometimes the Greek letter epsilon is used for that. And we're just going to try and fit the best line we can through a series of points. But we're going to do that through a mathematical tool. So how do we do that? So the way we do that is that we guess values for A and B, and then for each value, we compute the value of Y based on that guessed value of A and B. So here I've guessed a line and a slope, and then we're going to measure the distance between the value we guessed and the actual value. And then we're going to do that for every point. And we want to have the smallest error. So we're going to take each of these errors, we're going to add them up, and then we're going to minimize them. So the way we do that, we're going to use this equation here, which is the difference between the actual Y and what we forecast the Y using our guessed values. We're going to square those, and then using this symbol here, which is a summation sign, we're going to add up all of those sum of squares. And then we're going to find the alpha and beta that minimizes that total error. So to do that, we're going to use Excel. So we've talked previously about why we think Excel is a good tool to use, mostly because it's really a widely used tool that has a lot of different power. And we believe, especially at high school level, students should get exposure to spreadsheets in general and Excel in particular. So here we have our spreadsheet, and what we've created is our equation that we have before, which is Y equals A plus B times X1 plus C times X2 plus an error. We have our regression parameters. Those are the A, B, and C that we're going to plug into this equation here. We've calculated our error, which is our price minus the model. So we're going to use this formula here with our guessed values. That's going to produce a model price. We're going to take the difference between those, between the model price and the actual price. And then we're going to take the sum of the square of those errors. So we're going to square all of these and add them up. Notice some of these are positive and some are negative, but once we square them, they're all going to be positive. So it's going to make it easier for us to minimize the differences while minimizing this value. We're then going to use a tool in Excel called Solver. And through Solver, we're going to set the objective function of minimizing this value by changing these values here. We're going to hit solve, and then when we get our values, we're going to hit OK. And so then we get an answer that the equation that minimizes the sum of the squares is 21,000 minus $1,000 roughly for each aid each year, and then roughly about 3 cents or 3 or 4 cents for every excess mile. And then, of course, there's going to be some difference so that the model isn't perfect each time. And you can see that the model values vary by $63, $1,200, $40. So it's a pretty good fit, but obviously not an exact match. So we want to see how good a match that is. And one of the things that we can do is something called an R-squared. An R-squared is a measure of model fit, and it can be computed by taking the variance of the errors, that's the distance between each dot and the line, and then the variance of the actuals, which is just how much the dots vary by overall. And this particular model has an R-squared of 93%, which means that the model explains 93% of the variance of the car prices. And we can see that looks like a pretty good model. So it's not perfect, which would be 100% R-squared, but it's a very good model, and it's really giving us some insight into the value of cars based on the year and the mileage. So how do we use that? We can use it to make a prediction. So let's say Bobby has a 3-year-old car with 20,000 miles, which is about 10,000 miles fewer than usual. What's its estimated value? So we take the price of 21,000, we multiply the 1,000 times 3, that's going to reduce it by 3 years, but he has fewer miles times the negative, so that's actually going to add value to the car and give us a value of about $18,000 for this car. So would you buy the car for $18,000? Should Bobby sell it for $18,000? Well, why or why not? Well, first, remember that the model wasn't perfect, that we had some error. And two, we really don't know anything else about this car other than its age and the number of miles. Perhaps the car was in an accident, it has some dents on it, and that could reduce the value. Or perhaps Bobby has recently repainted the car and it has, it looks very attractive and someone's willing to pay extra for the car. So we really would need more information to make a final decision about the price of the car. I want you to keep that in mind when we talk about credit scores. Credit scores are based on certain data and they're used to make certain decisions. But the data isn't all of the possible data about you or any other borrower. And so therefore, it's not a complete picture, but it still might be useful. So in our next section, we're going to have a different type of model, and we're going to look at whether or not you would be late for getting to the airport. I hope you'll join us for part 3 of our discussion of credit scores. In the meantime, if you want more information about Bicycle, please go to this QR code. Thank you. We'll see you soon.